So hi everyone. Firstly, I'd like to acknowledge the traditional owners of country, the Gadigal peoples of the Eora Nation, upon whose land the University of Sydney now stands. Would also like to pay respect to the elders, both past and present, acknowledging them as the traditional custodians of knowledge for this land. Thank you everyone for joining us for National Science Week lunch talks at the Chowchak Wing Museum. And I'm really excited to introduce Sophie Cottam, who gives the talk up close and personal with the past nanoscale analysis of artifacts to tell us a little bit more about scanning electron microscopy and its uses. Sophie is a PhD candidate here at the University of Sydney within the School of Physics, studying plasma technology and its uses in vitro cellular studies. She is also a postgraduate teaching fellow in the School of Physics. And Sophie completed a Bachelor of Advanced Studies with honours in physics at the University of Sydney, and also a double degree with a Bachelor's of Mathematics and Bachelor's of Science at the University of Newcastle. And thank you, Sophie.
Thank you, Lorraine. So as Lorraine said, hi everyone. I'm Sophie. I'm from the School of Physics and welcome to Science Week at the Chowchak Wing Museum. Today, we're going to look into electron microscopy. It might be a bit different from the microscopes we usually use around the lab, and we're not using light here. It's solely based on electrons. And we're going to see what applications bringing together physics and the museum and looking at how our analysis of artifacts could help inform maybe the collections around the space. So through the talk, we're going to go over a couple of things. First of all, how do we even look at things without light? How do we use electrons to create these images? And then we're going to do what everyone tells us not to do, and we're going to judge something exactly how we see it. We're going to judge a book by its cover. After that, we're going to delve a little bit deeper and look into the compositional analysis of a sample. What makes it up? What elements are an artifact made of? So before we go into the analysis of the scanning electron microscope even more deeply through the talk, let's first discuss electrons and where they're found. Let's first discuss why we would use electrons to image a sample. So generally, when you've used a microscope, maybe in school or around a lab, we use light to illuminate our sample. And that could be done from the bottom or from the top of a sample. And we observe how that light interacts with the sample's surface and look at the surface features. Electron microscopy does kind of a similar thing. We illuminate our sample with electrons. So we shoot a beam of electrons at the sample and we observe how those electrons interact with the sample. But not only does this give us kind of an image of the surface structure, but we can look more at the chemical composition and makeup of the sample as well. Now, we can't see electrons with our eyeballs. So instead of observing the electrons directly, what we do is the electrons are captured by a detector and we look at the intensity of certain parts of the image and where it's been detected and make an image out of that. And so we observe that formed image, not the electrons themselves. So what is an electron? Well, you've probably seen some diagram like this, maybe on the hit show Big Bang Theory somewhere. This is an atom. And in the center of the atom, the big glob of red and blue bubbles that are stuck together, that's the nucleus. And those are protons and neutrons, positively charged protons and neutral neutrons, all housed together in the center in the nucleus. And around it, spinning like our planets orbit the sun, those are our electrons. Those are the things that we shoot at our sample and observe. So I'm a physicist. I'm lazy. All physicists are lazy. We like the path of least resistance. I'm going to simplify this diagram because even though it only has 3 components, it's way too complicated. Let's look at more circles. In the middle, we've got our nucleus. It's just the big white circle there. And then orbiting our nucleus at different distances away in different orbits, those little black dots, those are our electrons. Now, I like to think of an atom like as you would being at home or going on holiday. These electrons that are in an orbit closer to the nucleus, those are chilling at home. They're low energy. They're on the couch. They're watching their favorite movie. When you go up to a higher orbit, further away from the nucleus, that's when you're going on holiday. You're excited. You're, woo, let's go, right? So these electrons on the outer shells, those are actually high energy electrons. And this is really important to remember throughout our talk, because it's those different energies that give us different information about a sample, like what it's actually comprised of in terms of elements. So first, before we go into elements and what makes up them, let's just look at it on the surface level. And the way that we do this is with our electrons shooting at the sample is through a very specific interaction we detect as a secondary electron. So what happens here is our incident beam comes into a sample. It looks at an atom that makes up the material or the artifact, and it knocks out one of the electrons, the one that comes in knocks out one of the electrons that's already in this atom. And that electron that gets knocked out goes back off, and that's the one that we detect with our detector. And we look at the image that's formed from this electron. Now, you can imagine there's a lot of atoms across an artifact surface or a sample surface, because atoms, they make up everything. So this reaction happens quite a lot. And because it happens all over the surface, we can map surface structural features, and we can take a look at what might be on the surface in terms of dust. So before we jump into looking at things at such a microscopic level on the surface, I would like everyone to make sure that we're in the same frame of reference, and we're all going to grab some tools. Now, I know I didn't tell you to bring anything here today, but you already have it on you. It's a hair. So you pull out a hair from the head, or maybe look at one on your arm. And we're just going to keep this in mind as we go through our talk. And maybe look at your hair. What do you notice on it? Not much. It's very small, right? And we can't see much detail. But as we go into the images that are formed by electron microscopes, we see different things on the hair. And this is actually my hair. I've sacrificed myself for science. It's here. And you can see how small, and we can see dust particles, maybe what shampoo I've been using on these hair fibers. And we can even go in further and see the scales and maybe how the hair was growing and how well it was growing. So make sure you keep your reference hairs on you, okay? You all have them, no excuses. Now we know how big things are moving forward. And we can jump in and look at a few different surface structures. So like I said before, we get down to very small scales in electron microscopy, and we can notice maybe on artifacts differences in size between, let's say, if two artifacts were made of different materials, maybe what their grain structure looked like. We can look at tiny details that we might not see, like we just did before with our hair and the scales on the hair. And we can look at certain roughnesses on samples, which might show us how something was made or what it was used for. So here in the museum, we actually have a collection in the Macleay collection of mats that come from origins in the Pacific Islands, and they're tapper mats. And these are generally made of bark or grass materials. And some of these mats were given to me to look at under the electron microscope. So maybe we can go on a journey and look at some of these mats together, and you can get really close to something you might be able to go and have a look at after this talk. Now, these mats were given to me from curators and conservators who have specific research questions that might be answered by looking at these mats closer, and then they can inform the museum curators about what was happening in the past lives, or what the handling of the sample has been so far before it came to the museum. So upon looking closer at the grass mat sample, we can see the cellular structure of the actual grass that makes up the mat. And so you can imagine if we had mats that were made of different materials, this cellular structure might look different, and we could better inform our knowledge of what materials we use to construct these mats, which might differ from place to place around the Pacific. We can get even closer and maybe see the different arrangements of the cells. And not only this in certain parts of the mat, but we look at the intersection of fibers in the mats and potentially map out some types of adhesives that were used to create these materials. Actually, in some indigenous culture, indigenous tribes in Australia, they've used some spinifex grass and ground it up, and you can see those fibers that are used in adhesives under SEM. And so we can inform ourselves maybe what some historical uses of adhesives or how the adhesives were made, and we can learn more about those. So we can get really up close and have a look at the dust and other things on the surface that might inform us about certain artifacts. Now, these up close images can not only inform us of how the materials were made, but how they were stored when they were traveling from museum to museum. We can look at the top side and the bottom side and understand a bit more of maybe how these mats might have been used when they were originally made. Were they hung up? Were they put on the ground? And then we can also look at we can also better inform ourselves of how they might be treated and displayed in the museum. Now, I was given 2 samples of grass mat, and when I looked at the second sample, it had some fibers that maybe weren't on the other mat and looked not like grass fibers. Make sure you bring out your reference hairs now. This is not hair. It's very, very, very small compared to hair. But maybe if we don't have any biologists in the audience, maybe don't give your guesses first, but can anyone guess what this might be? It's okay if we don't guess initially. I'll zoom out. Maybe we can guess now. Lichen? Close. Yes, very close. I'll zoom out once more. You might be thinking we're scuba diving at the Barrier Reef right now, but we're not. This is actually mold on the mat, and it's infested the mat, and we can see maybe what type of mold. If you're a biologist, like I said before, physicists, I can't really tell that. We'll hand it over to our friends later and maybe figure it out. But we can inform ourselves as what mold might be on certain artifacts and this artifact, and that can tell us a few things. First of all, in the past, if we find mold on samples, this is not my SEM image, but this is an image of a dinosaur bone. I wish I got to image dinosaur bones. But this is some actual fossilized mycelia, which is the little dangly things on the end of the mold. And this can be found in bones, and it might inform us of what mold was available at the time a dinosaur was around. And we can place those dinosaurs in some layer of rock that was deposited at some point in time. And we can figure out, okay, well, if the mold was growing at that point in time, it must have had the right humidity and the right temperature to thrive. Otherwise, there might have been the right, there might have been some type of disease running rampant, some type of bacterial infection that became fossilized in the dinosaur. And we can map out what type of ecosystems, and we can really paint a picture of what was happening at that point in time in the past. But not only can mold inform us of the past, but it can help us in the present. This is what happens if we let moldy artifacts into the museum. Not only the museum artifacts that are on display now, but there's a lot of artifacts that aren't on display in storage, right? And so if we let some mold into that space, we could destroy thousands of very expensive and very rare artifacts that we definitely don't want to destroy, yeah? So by knowing that there's a certain type of mold on a sample, we can implement the right procedures for decontaminating that and improve our biosecurity in the museum. But we can also make sure, okay, how long do we have to quarantine this mold for? And really reduce the risk of this spreading all the way throughout the museum, yeah? So not only can we solve the museum's problems right now and not destroy the entire collection, but we can also build museums based on how a mold might be found and analyzed under SEM. So take, for instance, large archaeological dig sites, like the Terracotta Army in China. Those archaeological sites actually generally have museums built around them because they're large structures and we can't move it here. So what happens is if there's any mold growing, we can take samples of that mold, have a look at it under our electron microscope. We can figure out what type of mold it is, what environment it likes to thrive in, and then we can counter that by planning the design of our museum to minimize those conditions and not allow the mold to propagate throughout the whole site. So mold helps us not only on our blue cheese, but in the past, in the present, and in the future. Yeah. So also, if we look even deeper into the mold, and you can see everyone's got their reference hairs. We're at a very small scale here. There's these deflated footballs. Let's stay on theme for the current time, soccer balls, if you will. And that's really interesting because I also found these on another sample that didn't have this visible mold on it. So could anyone maybe tell me what these pea-looking things are? Yeah, exactly. You can see the spores from the mold, and they're actually growing off parts of the mycelium. Yeah, exactly. Good guess. And you can see that, yeah, these are growing off the mold, and they actually have a really hard exterior that can survive a lot of conditions. So they hang around for a long time. They hang around and move around so much that they've migrated from the non-moldy specimen of grass mat to from the moldy specimen of grass mat, sorry, to the non-moldy specimen. So by using scanning electron microscope, even though the mold is non-visible on this mat, we can see with electrons and make sure that those spores don't get into the museum. Yeah. So not only are spores able to be detected, but scanning electron microscopy can allow us to look closer at pollen as well. So the propagation of pollen happens when something comes in close proximity to a pollinating plant, be it the pollen travels by wind, maybe an animal eats the plant, drops it off somewhere else, or someone comes into direct contact with this type of plant. And all the pollen, you can see here little diagrams, they have extremely different shapes, and we can observe that under our microscope and kind of track the pollen from where it's been to where it is now. And that's actually a whole field of science, palynology. And we can track different types of pollen and maybe where they're deposited in different types of rock, like we did with our mold before. And we can figure out when the seasons were, what plants flowered in certain seasons in the past. Maybe we can map out what types of crops were grown in certain areas. We could map migration because one pollen ends up miles away in a different place that it shouldn't be. And we can do this to also identify maybe what our artifacts were used for in terms of that crop propagation. Now, not only is palynology useful for museums, but we can use it to solve crimes. Now, forensic palynology, that's a very small, there's not a lot of people keen on these jobs for some reason. I don't know why. You have to be an FBI agent that's really into gardening or a botanist that really loves true crime. And for some reason, those don't line up. So there's a lot of spots if you want a job in this area. But because pollen has such different shape, it's exactly like if we were to look at someone's fingerprint and we can track it back to the exact plant. Actually, quite recently, a break-in was solved. They had no substantial evidence for the accused to show that they did in fact break into the house, but they called in a trusty forensic palynologist and they looked at the accused's coat and it was covered in pollen, absolutely covered. And they said, hold on a second, this could not have happened unless the accused ran past a bush that happened to be placed next to the window where the break-in occurred. And from that, they solved the crime. And not only can we solve crimes, but we can use that same methodology to trace back our artifacts to where they were from and where they might be used. So, because there's not a lot of people in this field, I thought now is a really great time to conduct an interview if you were all trying to field. So if we could all stand up. Hopefully we do have some true crime lovers and some plant people in here. We're going to conduct our first round of interviews by guessing what type of pollen this is from. And we've imaged it under the electron microscope. There's your hair width for reference. You can grab it out if you need it for this interview. For A, I'd like you to put your hands on your head. B, hands on your hips. And C, sit down. Could we maybe try guess what pollen this is? All right, guys, it's just the start of my talk. You shouldn't be sitting down. It's a grevillea, okay? Come on, get involved. All right, okay, I guess some of us made it through the first round of interviews. Here's the next pollen up on the list. Is this A, cucumber, hands on our heads, B, rhubarb, hands on our hips, or C, tiny footballs? Maybe the other type of football that's not, trending right now. All right. Now we're pretty onto it today. This is in fact rhubarb. So good on to everyone looking very cross at me right now. Okay, final one. This one's a bit trickier. We've got A, pineapple, B, passion fruit, and C, pumpkin. If you don't know where to put your hands now, I'm sorry, you're not making it through the interview process. Okay, come on, you've had 2 goes already. What do we think this pollen is? Right, everyone's locked in their answer. All right, it's pumpkin. You should be sitting down. We're going to continue the talk now. All right, so hopefully through that interview process, you've now come to appreciate how different pollen structures look and how different they look at the scale our electron microscopes can get to. Now, from this, we can look at our tools and look for these traces of pollen, and then, like I've mentioned before, trace it back to their uses. Not only can we just look at pollen surfaces, but we can look at the surfaces themselves. So I have 3 images here. One is not like the others. Do I have any brave volunteers to try and pick out which one is different to the others? Maybe tell me why. Yes, Sarah. Why would you say it looks different? In these ones? Yeah. So Sarah's right. Over in these 2 sections here, you can see there's a lot of holes. It's quite a porous structure, or maybe there's kind of like a fur growth pattern happening here. These 2 on the left are actually bones, and on the right here is dirt, just plain old dirt. And you can see the difference, the immediate difference in surface structure and that information that it could give us in terms of looking at our artifacts and what they're made of. Now, this is all done with secondary electron scanning microscopy, but sometimes just looking at the surface doesn't cut it. We have to get deeper and we have to look at maybe the differences in what an artifact's made of. The way we do this is using backscattered electron imaging. It's a different mode of interaction with the electrons that we shoot at the sample surface. And in this interaction, the electrons that come down see the atom. The atom says, no way, Jose, you are not knocking out one of my electrons today. And then the electron goes, okay, Uno reverse, heads back to the detector. And so we detect the exact same electron that we've sent into the sample. Using that, because that interaction with the atom will be different every time for different elements, we can map the composition of a sample. So this is our mold in our secondary electron image. So like before, we discussed, it looks at kind of the surface structure. And if we go into backscattered electron imaging, you can see that it all kind of shows up as the same color. That's expected. Hopefully mold is growing and made out of the same thing. It's all carbon-based, it's all organic. But if we move to something that might have a bit of different elemental makeup, we can see on the left secondary electron, there's not too much differentiation between different structures. But on the right, you can see that this crystal structure is definitely made of something different to the grass mat that's behind it. So this is some salt on the grass mat surface, and this could let us or inform us whereabouts a sample might have been located in terms of if it was on the coast or in different mineral areas around the space. So not only can we use it to look for different salt structures and different elements, but we can look for impurities and contaminants that might be on a surface. And these might have come not from where the sample was made, but also from previous treatments that a museum might have done before they give the artifact to another museum. Because like we've said before, we want to get rid of the mold. Maybe there's been a treatment that's been done to reduce that. And not only that, we can better map areas on the sample that might throw us off the scent if we're trying to investigate the elemental composition a bit more, like dirt on a piece of bone, for instance. So backscattered electrons really inform us on the different elements that make up a sample. But how do we dig into that even deeper and know what each element is? The way we do that is with elemental mapping, and we can do this from an interaction with the atom that produces an X-ray. So we're putting electrons in and we're looking at the X-rays that come out. How might this happen? Well, similarly, with our secondary electron mode, we shoot an electron at a material. It comes upon an atom. It knocks out one of the electrons in the clouds around it, and it leaves a hole in the atom. Like a hole in your heart, you want to fill that. Yeah. And like I said before, the electrons close to the nucleus, that's like you chilling at home on the couch. And if you think about it, sometimes at the end of a holiday, you really want to come home to your own bed. So the electron that's out on holiday at a higher energy level comes back closer to the nucleus in the atom. And sometimes it takes a lot of energy to get home, right? You have to catch a lot of flights and then the train home, it takes a lot of energy. So that energy is given off as a ray of light, but we can't see that ray of light. It's way, way, way too high energy for us to see. That's actually an X-ray. And so we detect the energy of the X-ray that's given off, and that will be different for different elements. And then we can go, oh, that's definitely this element in the surface. So for example, if we look at the grass mat and we look at the bulk structure of the grass mat, we can look at the X-rays and determine that most of the X-rays are coming from carbon and some are coming from oxygen, which is what we assume for like an organic type of material. If we go to this contamination that we saw before in our backscattered electron mode, we can see here that we have carbon, oxygen, which might be coming from the background of the surrounding mat. But we also have nickel, copper, and zinc. And this might inform us of what tools were used to either make the mat or what processes and pigments might have been used to dye the mat, as well as different decontamination processes between museums. So we can use our backscattered electron to find the contaminants, and then we can address it by looking at the X-rays that come out. Do this? Well, we dig up a lot of samples and they've been in the dirt for a while. They all look the same, right? There's years of dirt. We don't know what they are unless we look at the elemental makeup of the sample. Again, like I said before, we can look at previous treatments that might have been done from museum to museum, and we can make sure we avoid any misreading of the sample surface structure that might have occurred over time due to some chemistry change. Think of how a nail might rust over time. We can avoid that. Not only that, but because we now know what the sample is made up of, we can make sure that we implement the right restoration procedures, because we wouldn't want to mix two chemicals together that might ruin the artifact. Yeah. So let's look at a place that we might actually use this. And this is in Tasmania, a site that's around 19th century army barracks, thought to be army barracks. And this site is actually visited by the schools of archaeology here at UCID and also at the Australian National University. And it's used as like a little fieldwork school where archaeologists in training can practice their skills and learn how to identify objects around a historical site. It's actually a really interesting site because on this site, we had convicts that were originally brought here. And it's a site of transitional change because these convicts started to gain an independence and form their own agricultural practices around the area. So it's really interesting to look at maybe what items were used during this period and form an image of what the lives of the people that lived here might, what the lives might look like. So we were given some bones from this site. And why might bones be interesting? Well, they will tell us about what livestock the people around this site were eating at the time, or if they could even have livestock. If they were in the army, maybe they were eating certain rations. It would also give us insight into if there are any mouse bones around, if they had good hygiene or not, something that we might not think of just by looking at bones. But not only that, we can figure out, okay, if there were certain bones around, what were they eating? Were the rations not enough? Did they have to go hunt other things or grow their own or culture their own livestock to feed themselves? And not only does that give us an insight to what they were eating, but by knowing what they were eating, what cuts of meat, if they were eating the mice that they found because they had poor hygiene, that can give us insight to how much money they had. If they went and got a good cut of meat and we see a T-bone steak bone lying around, then we know that they had enough money to afford that. And we can really start to form a picture of what the past lives looked like. So for reference, before we journey into some analysis of the samples from this site, this is what the composition of bone looks like. It's organic. We've got carbon and oxygen, as we would expect. But then we also have phosphorus and calcium, which in our body, the largest deposits of phosphorus and calcium is actually in our bones. So moving forward, we can use this to avoid, when we get a sample, misidentification of this. And remember, I'm a student. The people on this archaeological site are also students. We make mistakes, okay? So it's good to double check what our samples are actually made of, because the first step in archaeology is kind of sorting samples into bone, ceramic, or stone materials. So it's good to really confirm down the first step of our procedure. It also allows us to remove any personal misinterpretations that might happen, because something might really look like a bone, but actually it was from another artifact that was around. So the first step in our procedure to identify artifacts is to look at the surrounding dirt, because bones, we're digging them up from the ground, they're caked in dirt. So you can see here on this bone, if we look at the dirt structure, which we identified using our secondary electrons looking at the surface, we can see that we've got a lot of aluminium and a lot of silicon in our surrounding environment. Yeah. So then when we move to the bone structure, we can see that, yes, we might still have aluminium and silicon, but this is probably not due to our sample, it's due to the surrounding environment. And we can instead look at the fact that we found phosphorus and calcium, and we've got a bone here as our artifact. So I was also given an unknown sample, so none of the students on this trip could identify it. There's an argument going around that it might be a pipe, it might be a piece of bone. And why would it be a piece of pipe? Well, in the days where this historic site was stemming from, originally they would use smoking pipes or tobacco pipes, maybe to socialize, maybe to just use around the site. But by mapping where certain artifacts were found, like these ceramic pipes, we might be able to find out where the more social parts of the site were, or where if we find more bones, what was used for the kitchen, or where things were maybe our livestock was slaughtered, and we can figure out mapping about the site and what rooms were located where, and we can find out just more about the lives of the people who lived in these buildings. So if we look at the sample that was unknown up close, we can see in backscattered electron mode, there's a difference in the contaminants, the surface contaminants, the dirt, compared to the underlying bone. And if we look at that, we're getting our characteristic aluminium and silicon, which we know was in the surrounding dirt already. And this is from the same archaeological site, so we can assume it's the same dirt, yeah? And we're getting traces of phosphorus and calcium already. Why might that be? Well, we're looking at quite a thin layer of dirt here. So maybe we're getting contamination from behind, from the underlying bone. So if we move now to more a less contaminated piece of bone, we can see that we're getting everything we assume to get from bone, phosphorus, calcium, but now I have tellurium. That's kind of weird. Why do I have tellurium? Well, tellurium is a heavy metal, and generally over our lifetime, heavy metals tend to start moving towards our bones and are stored in our bones. So not only am I certain, or quite certain, that this is bone by looking at it, but we can tell that this bone has come from maybe an older organism that's had time and has had a time in its life for this heavy metal to actually start concentrating at the bones. So we get a few things from this. We get, yay, it's bone, it's not ceramic, and we also can start to form a story that this is an older animal. Maybe animals were raised on this property and they're not just, I don't know, coming on and using the young and getting them as fast as they can. So we can have a look around and see what else was happening at this historic site. So that brings us to the end of the talk. We've learned a lot today. We've covered a lot. We found out that we don't need light to see. We can just see things with electrons. And we've learned that pollen can solve crimes. It's not just the bees that love it. The forensic paleontologists out there, make sure you chase up that career path. Mold, you know, we don't just eat it on our blue cheese. It can be used to design museums as well. And mistakes happen. I'm a student. We love to avoid misidentification. We like to make sure we're sure of ourselves. So electron microscopy, unlike our light microscopy, can actually give us that certainty and eliminate bias. So yeah, I hope I showed you today that physics and museums should collaborate more often, and there's way more to get out of electron microscopy than meets the eye. Any questions? All good, all good. No? Cool. Yeah. Yes. That is a very good question. I myself am not a paleontologist, but assuming certain pollens might be also found in certain deposits in the rock, that you could map those back to certain times. And if it was ancient pollen, you would assume that it's not picked up on the way to the museum. Yeah, but that's something for a paleontologist to address. So maybe go find one of those people. Sorry. Yeah. Yeah. That's all the physics I can help with. Yeah.